All right. Hello, everyone. Welcome back for another lecture. This one on gauges or gauge theory, which, as Michael has already explained to some degree, is important when we want to define convolutions on manifolds, and also when we want to deal with signals that are actually fields, things like vector fields and so on. Now, gauge theory is a very important and fundamental topic in physics, and it's also notoriously difficult to understand. So for me, it took maybe a year for me to feel like I had a reasonably satisfactory understanding of the topic. And still now, I have a lot to learn. You can really spend your whole life learning about this. So after you've had a whirlwind tour of differential geometry from Michael this morning, I'm going to give you a whirlwind tour of gauge theory. But similar to what Michael said, it's not realistic to really give you a formal introduction. So it's going to be mainly on an intuitive level, though I'll try to give some of the mathematical flavor of this theory. So here's the outline for the talk today. I will start with some motivation. So why do we need to study gauge theory if we're interested in geometric deep learning? The main answers are that we want to deal with these feature fields, and I'll give some examples of how those occur in real data, as well as we also needed to deal with this problem of orienting the kernel when you're doing convolution on manifolds. Then I'll talk about Gauge-equivariant convolution on manifolds and meshes. And at the end, if there's time, I'll talk a little bit about the mathematical theory, namely the theory of Fibre bundles, which is how the mathematicians basically formalized gauge theory. So we'll look at from the Fibre bundle perspective, what is a bundle, what are gauges and gauge transformations, both so-called internal gauge transformations, which have to do, well, I'll explain later what that means, internal and external gauge symmetries, and what gauge equivariance means. All right, so before we go to the motivation, just to make sure we're on the same page, let's look at what a gauge and a gauge transformation is again. This is, as is some of the other stuff in this talk, is going to be somewhat redundant with what Michael explained, but again, because this subject is rather difficult, I think it's actually useful to repeat a little bit. The general picture that we have is we have a manifold. In this case, I've drawn a sphere, and on each point in this manifold, we have attached some vector space. The typical example, and the one you should think of here, is the tangent space at each point. And for each tangent plane, there's a large number of frames that we could consider. A frame being a basis with ordered basis vectors. So here we've drawn so a gauge is then a choice of frame for each point in some region of your manifold. Perhaps the whole manifold, if that's possible, or perhaps some local region U1 or U2 in this case, where the red and the blue gauges are drawn. Couple things to notice. Firstly, here, the way I've drawn this is I've drawn a couple coordinate lines on the manifold. These are the thin lines in red and blue that you can see here. And we've chosen our gauge such that they align with the coordinate lines. But it's important to keep these things separate. So the coordinates, they allow you to pick a point on the manifold by choosing some coordinates. So this point has certain latitude and longitude, for example, that allows us to identify it. But the gauge really pertains to directions in the tangent space. And you can choose them to be aligned with the coordinate lines, but you don't necessarily have to. So that's just a special property of this drawing here. And in general, in this talk, I won't discuss coordinates of the manifold very much. All right, so yeah, the other thing to notice, as I already mentioned, the gauge will typically be local, so it will not always be defined on the whole manifold. And so you work with multiple gauges. And that means that if you have a particular tangent vector, like the green one here, it can be represented in multiple gauges. In this case, we have a red and a blue gauge. And perhaps in the red gauge, this vector might be represented as 1, 2. And in the blue gauge, it would be represented as 2, 1. But even though these numerical descriptions are different, if we remember what gauge was used to describe it, we see that the underlying vector, the green thing that lives here on the manifold itself, is the same. And so changing from one gauge to another, from red to blue, for instance, that's what we call a gauge transformation. And it can act on the numerical description of the vector to give you the numerical description of the same vector in a different gauge. So it's important to realize that this notion of gauge transformation, well, it's a very flexible kind of thing. The gauge transformation has many degrees of freedom because we can essentially freely choose at each point in the manifold how we want to change our gauge. So that's a lot more degrees of freedom than if you were to just consider, let's say, a single rotation or a single linear transformation. All right, so that's the general idea. So let's look at why we are so interested in this. So the first thing that I'll mention is feature fields. So in many scientific domains, you'll find data that is naturally understood as a field on a manifold. So one example would be if you're doing analysis of global weather data or climate data. Your manifold is a sphere, that's the Earth, and you might your measurements might be something like wind directions on Earth. So that's a vector field as drawn here. And so if we want to define a convolutional network that can process this, it should understand vector fields, and it should understand how vector fields transform under symmetries like rotations. Another nice example is tensor fields. They occur, for instance, in so-called diffusion tensor imaging. So the word tensor is a fancy one, but but here it basically just means a 3x3 matrix. So in a diffusion tensor image, typically it's a form of MRI, typically applied to the brain. And what it measures is at each point in the three-dimensional space, it measures the diffusion in each of in every direction, essentially. And that's represented as a 3x3 matrix whose eigenvectors are the sort of the principal directions along which the diffusion happens, and the eigenvalues are the strength along which that happens. And so if you're familiar with the geometry of eigenvectors and eigenvalues, maybe from PCA, you know that you can visualize this as an ellipse, as done here. And so these are tensor fields, and these tensors are also represented relative to a gauge, and it can be helpful even though there's a natural standard gauge where at every point there's an XYZ direction that's globally consistent. Even though that is the case, it can be very useful to consider gauge symmetries, as we'll see later. So there's another reason why it's useful to consider this notion of feature fields, even if your data comes in the form of scalar fields. And for this, you can think back, for example, to the lectures on spherical CNNs, where we started with a scalar signal on the sphere, and we saw that our convolution, our group convolution, would produce a feature map on SO3. Now, SO3 is a three-dimensional manifold, and so convolving on it is actually pretty expensive. And more generally, as your group becomes higher dimensional, or in the discrete case, just larger, doing a group convolution on the whole group can be much more expensive. On the other hand, we also saw if we want to stay on the homogeneous space itself, if we want to, for example, work only with scalar signals on the sphere, then that implies that we need to use isotropic kernels, so kernels that are rotation invariant, and that is also very limiting. So by using feature fields, like for example, having your feature maps internal to the network be vector fields or tensor fields or something else, you have some intermediate solution where your kernel is less constrained and your features are a bit more expressive than scalars, but you don't pay the full computational cost of convolving on the group. All right, this is a recap from a previous lecture. So we recall that a function is something that maps a point U, and here we consider functions on omega. So it maps a point U in our domain omega to a value x of U in some feature space C. For instance, it maps the plane to an RGB value. A field is slightly different in that it maps a point in the base space or in the domain omega to a point xu, which lives in a space that is itself parameterized by u. So again, the tangent plane is an example. For every point on the manifold, there's a different tangent plane, and although they all look alike in that they're all two-dimensional, in this case, two-dimensional vector spaces, they are not the same. Mathematical way to say it is they are isomorphic, but not canonically isomorphic. There are many ways to align them. So if we want to describe a field as a function, what we need to do is we need to align all of these things, CU, these are called fibers, with a canonical fiber that we can take to be, let's say R to the C for a feature with C channels. And to align basically means we have to choose a linear invertible map, WU, sometimes denoted omega U, that maps from RC, from our coordinate space, to CU. And ideally we would want this to be smooth in U. So that is one way to define what it means to choose a gauge. We want to choose for each point U a linear invertible map from our coordinate space or our canonical fiber R to the C to the fiber over U. So choosing 2D coordinates is essentially the same as choosing an X and Y axis here, because you can map the standard basis of R to the C to our space CU. So that's what we mean by choosing a gauge. Now, in some cases, there's an obvious choice of gauge. So if you have if we have our plane R2, that comes with a standard basis 1,0 and 0,1. And because of the special properties of the plane, we can sort of translate that frame to every other point. That gives us a global gauge, simultaneous choice of frame at every point in our manifold. That feels sort of natural to our eye. Although, of course, in some applications, even there's nothing special about the X and Y directions. And so this is not even a natural choice. In other cases, like the sphere, there really isn't a natural choice at all. And so that's a very important thing to realize. This choice of gauge is completely arbitrary. And so how our data ends up being represented in computer memory is also in a way arbitrary. And we need to develop methods that are somehow not affected by this arbitrariness, which we'll see takes the form of gauge equivariance. So another thing to realize, again, Michael touched on this, is that a global, continuous, or smooth gauge may not exist. So here we have the donut, and this is a manifold that's parallelizable, meaning we can choose a smooth vector field that's defined everywhere, that doesn't have any singularities. And this vector field could serve, for example, as the x-axis of our field of frames. On some manifolds, that's not possible. So here you see, if we try to comb the sphere, we'll end up with some singularities where it's not, you cannot smoothly choose a vector at the North Pole here. So this necessitates the use of local gauges, at least in the mathematical theory. In practice, sometimes you can get away with just not caring about smoothness. We're going to have to discretize our manifold anyway. And so we could also just put some arbitrary frame here at the North Pole, and it will not be smooth. But as long as you take into account the fact that the frames at nearby points at this location are radically different, as long as you take that into account in your computations, you can build your network such that they're really not affected by the singularities. Nevertheless, from a mathematical perspective, that's very important, this locality. All right, so to summarize what we've learned so far, we've seen that geometric data in the form of feature fields can only be represented relative to a gauge. But in general, there is no natural gauge. So we have to make some arbitrary choices in order to represent data. Or in other words, the same field can be represented in many equivalent ways. Furthermore, in general, we cannot use a single gauge to represent a continuous field as a continuous function. So we need gauges in multiple charts. Yeah, I think the continuity aspect is quite important. If you don't take that into account, I think your learning algorithm will have a much more difficult time to generalize, because things that are actually similar, in the sense of the actual, let's say the actual vector field is similar, will look very different in terms of its numerical representation if you don't take this continuity into account. All right, so here again we see a gauge transformation, this time for the plane. We have here our nice regular gauge, and here we have another one which from a mathematical perspective is just as good a gauge as the first one. So you see at each point, we've applied a transformation. And in this case, all the gauges here are orthogonal. So the frames here are orthogonal, these two frame vectors, and similar for the new gauge. So what that means is that the new gauge at a certain point is always related to the old one by a rotation or potentially a reflection. In this case, I've also preserved the orientation. So all of these frames are related by a rotation. And so this defines what's called the structure group, denoted by G here. So this identifies the structure that we care to preserve. In the least restrictive case, we'll just preserve the linear structure. So you have a general linear group of invertible matrices. If you want to preserve the angles or orthogonality, you would have a structure group as the orthogonal group. If you furthermore want to preserve the orientation, then you would get a special orthogonal group. I'm a little bit confused. It says participants can now see your screen. I hope everything was visible before as well. If there's a problem, let me know. Otherwise, I'll just continue.
Yeah, there wasn't any problem.
Okay, thanks. All right, so the formal definition then of a gauge transformation is that it's a function G. So before we denoted a group element by G, now it's a function from our domain omega, or more generally from some subset of omega to our what's now called the structure group G. Typically, this will be just rotations of your frame. And the way that this acts on signals depends on what kind of signal it is. So we have x of u, that's some c-dimensional vector. And the way that this gauge transformation acts on it is via this representation rho. So in the case of the diffusion tensor images, there's a certain representation that says if I rotate my frame, how does this 3x3 matrix transform? If it's a vector, it transforms like a vector and so on. So there are different choices of representations, different kinds of fields that you can choose. And that's how this gauge transformation acts. But notice that the gauge transformation here is indexed by u, just like this field x. So at each point, it's different. All right, so here we have our example again, diffusion tensor images. So we can model a DTI signal as a function x from r to the 3 to r to the 3x3. In this case, we don't have to worry about sections because this in this case we can align all the tangent spaces of this manifold. So we can describe our signal as a function. The representation that we have here may remind you of what we saw with the adjacency matrices for graphs, where we had a permutation that acted by conjugation on the rows and columns of this matrix. In this case, we have a rotation matrix R, and the way it acts on our matrix M, this 3x3 matrix, is also by conjugation. So you're changing the basis on a matrix. Now, one thing to realize is that this row is actually a bit different than the types of row I've described before, where we described how the global signal transforms. This is a representation row that acts only on a single 3x3 matrix. Now, we could use a translation and maybe a rotation equivariant convolutional net, but you can wonder if that's actually appropriate for this type of data, because the brain is typically registered, so it's in a standard position. It's in the center of the image, and it's in upright position. So we can say there's not really a global rotational symmetry in this problem. However, at small scales, you can imagine the structure of the brain, that certain local features will occur in every possible orientation, with every possible rotation applied to it with equal frequency. So we may assume that all local directions at each point should be considered equivalent, while we still want to distinguish different angles. So we want to preserve angles. So another way to say that is that all orthogonal frames should be considered equivalent, or in other words, we have a structure group G equal to O3, the orthogonal group in 3 dimensions that contains rotations and flips. So now our gauge transformations, they correspond to mappings G from our domain omega, or R3 in this case, to O3. So it picks at each position in 3 space a rotation and reflection matrix. And it acts on these fields via this representation rho, that is to say, by conjugation of the matrix M, or the matrix M being this X at U. X outputs this matrix. All right, I hope that's clear. So then we have gauge equivariance. So here we have again the example of a vector field. In the bottom left, I've drawn an input vector field expressed relative to a standard gauge. And if we were to apply the gauge transformation, and we want to describe the same vector field, we know once again that our numerical representation will change, but the underlying vector field doesn't. I apologize for the bad graphics here, but I think you get the idea. Now, if we have some mapping F, let's say it's the layer of our neural network, it will take the coordinate representation of our input vector field and produce the coordinate representation of the output field, in this case, just a flip. And we would typically choose to represent the output field relative to the same gauge as the input field. And then what we would like is that if we apply gauge transformation to this output field that we've obtained on the left, again, we get some different numerical representation of the same field. Well, that should be the same as first applying this gauge transformation and then applying our mapping F. So that's the meaning of gauge equivariance. If F satisfies this property, it is gauge equivariant. So here's another a fun example. That is the first example of an internal gauge symmetry. So in the examples before, we were always talking about spatial directions, either tangent planes, or in the case of diffusion tensor imaging, the tensor is actually also defined in terms of the tangent space. So tensor is it's a tensor product of tangent vectors. So in other words, the dimensions of your fiber have some relation to the directions in the domain omega. Now here we have another example, namely a very familiar one if you've ever thought about computer vision, which is an RGB image. And mathematically, we modeled this as a function from R2, the plane, to R3. That's our RGB space. And now we could consider two kinds of gauge symmetries. It depends on the problem, whether you think either of these is appropriate. But the first we could consider is to say, we're going to assume that R, G, and B are equivalent. So in that case, we would choose a structure group G equals S3, the group of permutations of 3 elements. And it could do something like what's shown here on the right. We have our RGB values for a single pixel, and we can permute it in some arbitrary way. We can also consider all U values equivalent. So we would choose structure group SO2, which would rotate through the different colors of the rainbow, essentially. Now, it's important to realize that a gauge transformation will change every RGB pixel independently at each position. So if you did this, the numerical representation, once again, would change drastically. And if you were to then plot that image, interpreting the first coordinate as R, and then the second is G, and the third is B, you would get potentially complete garbage. So if you were to plot this, and also if you were to do any computation on this gauge transformed RGB image, you need to take into account the gauge transformation that was applied. You need to take it to remember for each pixel what is the order of red, green, and blue. Now, so far, this seems like a pretty pointless exercise, right? Why would you change arbitrarily the order of R, G, and B in every pixel? But if you assume that this gauge transformation is a symmetry, then you automatically, from the theory that we'll look at later this lecture, you get a constraint on your convolution kernel, which essentially says that each of the 3 colors has to be treated equivalently. In the same way that, let's say, a rotation equivariant net would treat every direction equivalently, this would treat every color equivalently. And so it could automatically generalize across colors of an object. All right, so the second motivation is if we just want to define convolutional manifolds, even if we start out with scalar signals. So we can think of various ways to define convolutional manifolds. And the first one is very natural if you've learned about homogeneous group convolution, like convolution on the sphere. So the idea there was that we define a kernel somewhere and we move it around the manifold by global symmetries, let's say rotations over the sphere or translations over the plane. That works fine in a homogeneous space where for any 2 points there is a transformation mapping one to the other. But on other spaces, there's no such, there's not always such a symmetry. So here you see a rather special shape, the icosahedron, and clearly we can look at, let's say, this blue patch, and there are symmetries of the icosahedron that will map this blue patch to, let's say, other corners of the shape, but it will never map it to the interior of a face where we see this red patch, for example. So the symmetries would not give us weight sharing between those positions. We can also try weight sharing via parallel transport, but again, as Michael explained, the parallel transport is dependent on the path. And so if we define our canonical filter here, where the black vector is situated, and we parallel transport it across this arc, we would end up with a filter oriented in one direction. If we were to transport along another arc, we would end up with a filter in a different orientation. So now we have some kind of arbitrariness with respect to how we choose paths, which seems undesirable. Here's another way to see the same. In a flat space, if we move a filter, it doesn't matter what path we choose. And in a curved space, it does matter. So it's maybe strange to call a cube curved, but actually it is curved in the sense that, for example, around the corner, you cannot flatten this piece of the manifold without cutting the shape. And you see if we take this filter here on the front face, we move it to the top like this, we end up with a filter in a different orientation than if we first move to the side and then to the top. We could, we could cut the shape. In this case, it's easy for a cube. We lay it out flat like this, and we just say, okay, we'll just use this orientation. We use a canonical gauge, a fixed gauge in this flattened shape. And this will work, but you will now have discontinuities along the edges that were cut. So if you think about this edge and this edge, for example, and you fold them back together, you see that actually the orientation of the filter changes, well, by a big step, by 90 degrees, even though the points on this edge, they're very close in the true shape. You don't see that when you cut it open, but these and this point and the points on these two edges are actually identical. But the way that these pixels gets filtered will be completely different by 90-degree rotation. So again, you're introducing discontinuities in your feature map, which aren't really there in the original signal or in the shape, which would be bad for generalization. Then another approach, again, Michael mentioned it, spectral convolution and graph convolution, where you use isotropic kernels. And so here you would circumvent the problem of the arbitrariness of how you orient your kernel by making it so that whatever orientation you choose, it's going to end up with the same filter. And that's a fine solution, but of course it's a bit limiting to only have isotropic kernels. Then the Geodesic Convolution, published in 2015 by Michael and colleagues, where the idea is that you're not going to choose a particular orientation for the filter, but you're just going to rotate your filter in every possible way, or maybe we discretize with some finite number of orientations, and we just compute the inner product with all these rotated copies of the filter and a local patch from the manifold. You may remember this from the lecture on group equivariant convolutions as a scalar to regular layer, we have a scalar input signal, and the output signal that has one channel for each orientation. We remember if we change the orientation of, let's say, the first filter and all the others along with it, then we would see a cyclic shift among the features. So it's not invariant to the orientation that you choose, but once you max pool over orientations, i.e. from some regular to scalar function, then you again get a scalar signal. And so you can repeat this kind of convolution layer. But this is still potentially undesirable, because now the features after max pooling will not contain any orientation information anymore. So in this case, we have some kind of edge detector, and after pooling, the feature can tell us that there is an edge here, but not what orientation it has. And that you can imagine how for some problems that's important, an important piece of information. So then here's the idea for gauge-equivariant networks. So the mathematical setup is as follows. We define for each layer a feature space, just like in our blueprint. We have a domain omega and a feature space C, the fiber, that we attach to each point U in omega. This fiber or feature vector is associated with the transformation law or group representation rho that determines how gauge transformations act on the feature vectors. Again, think of the example of tensors and vectors as two different ones, or scalars also, as they transform according to a trivial representation. They're invariant. Then our feature space is a space of rho fields over omega. So I think it's clear by now what that means. And mathematically, the technical jargon for this is a section of an associated bundle. And we'll look at that later. And then we seek a convolution layer that is gauge equivariant, meaning if we perform a gauge transformation, the coefficients described in the input will change. And so the coefficients computed as output must change accordingly. So let's first look at a simple case where the input is a scalar field. So we have here our setup. We have omega as an S-dimensional manifold, and we have a signal, scalar signal on the manifold. We have also a filter that, just like what Michael described, we can take this to live in the tangent space. So it's a function on Rs for our S-dimensional manifold to R. And we have, because this is expressed in terms of coordinates and not in terms of abstract tangent vectors, we need a gauge to map, to tell us how Rs, the tangent coordinates, are mapped to the tangent planes. So that's called a gauge. Yeah, and this is the cautionary note again about the smooth global gauge may not exist, but we'll ignore that for now. And we have again our exponential map that maps the tangent plane to the manifold. Then we can define a gauge-equivariant convolution like this. We integrate over the tangent plane, or rather over the coordinates of the tangent plane, the filter at that value times the signal at the value that, or the point that we get to by shooting a geodesic from V. So you see this in this diagram. We're at this point P. That's where we want to evaluate our convolution. Here we have a tangent plane at P. We have our tangent vector V, or in coordinates little v, and the exponential map gives us some neighbor in the vicinity of P that we get by shooting a geodesic in this direction for 1 unit time. Right, so that's how we can define this this convolution, and one can show that it is gauge equivariant with respect to the trivial representation that we have for scalars, if and only if the kernel satisfies this constraint. If for every g, every rotation in this case, applied to our coordinate vector, the value of the filter doesn't change, i.e. it's rotationally symmetric. So we recover here the isotropic convolution approach that we saw before. This is, it turns out, the most general kind of convolution if your input signal and output signal are both supposed to be scalar fields. So let's look at something more general. So now we have as input and output a more general field. And we'll assume for now that we can choose a global gauge that will make our life a bit easier. So we have a signal X, and because we have a global gauge, we can describe it as a function from omega to r to the C1. So we have C1 input channels, and we want C2 output channels. So our filter now is going to be actually a matrix valued function on the tangent plane with C2 output channels and C1 input channels. Again, we have a gauge, and we now need to consider the structure group. It becomes important. This is what you get if you change from one gauge to another. It should live in this group, and let's assume for now that this is the special orthogonal group. So we'll work with oriented orthogonal frames, and we need to choose now row 1 and row 2, which are representations of this structure group of dimensions C1 and C2 respectively. So maybe C1 is 2. We are considered a vector field. Row 1 is the way vectors transform, and row 2 is the way that 2 by 2 tensors transform. So that would be C2 would equal 4. We have this parallel transporter. Again, I think Michael covered this very well. So this tells us how we transport from the point we get to by, or the point indexed by V. So this one, the exponential of V to P. So what rotation will take place if we map from the coordinate vector at a coordinate vector at V to a coordinate vector at P that corresponds to the parallel transported vector. All right, so we now have a similar equation for the gauge-equivariant convolution for an input row 1 field to row 2 field, which looks like this. We again want to take some kind of integral over the tangent plane of our filter times our signal. But in addition, we now need to take care of the parallel transport, the fact that the output of X at this point, indexed by V, lives in a different fiber than the neighbor we get to from another V. So if we're going to add or integrate over all of these, it doesn't make sense to add vectors that live in different vector spaces. So we need to apply this parallel transport first, and then we can add multiply by the kernel and add everything up. And you can see that this operation is gauge equivariant if and only if the following equation holds. And this is an equation you might recognize from earlier lectures, where we also saw basically exactly the same thing appear for group equivariant convolutional nets. And you all can also see that this equation specializes to the one that we saw on the previous slide for the trivial representations, where row 2 of G and row 1 of G equal 1 for every G. So in the interest of time, I'm going to skip this, but if you want to do things the right way, you need to work with multiple local gauges. And the gauge equivariance actually makes sure that for points that lie in the intersection of two gauges or two charts, you're going to be essentially computing the same thing, just represented differently. So here, let's look at an actual practical example. So this is an example for the, here the shape we convolve over is the icosahedron. So this is a shape that fairly well approximates spherical signals. and it has some benefits because of its high regularity. We can implement the convolution on this shape in a very efficient way, as we'll see, leveraging the conv2d operation. Okay, so here on the left we have our shape. It's maybe technically not a manifold because it has sharp corners, but we can sort of ignore that. Let's call this a manifold. And we are going to cut it up into a number of charts. Here you see one chart indicated in gray, corresponds to the chart shown here in the bottom. And we have 5 other charts with similar shapes. And if we apply some kind of skew transformation to this triangular pixel grid, we can make it into a square pixel grid and squeeze everything into a nice rectangular array that allows us to easily perform computations. Now, one thing to notice is that as shown by the colors here, for instance, this red line, it is actually present. Some pixels are present in multiple charts. So the red pixels here correspond to the same red pixels in the chart right above it. And that's going to be important for the implementation of the gauge-equivariant convolution. Namely, so the general idea is going to be we store our signal like this in a rectangular array, and we're going to do convolution using a kernel that satisfies the kernel constraint. But ultimately, it's just a normal convolution on this 2-dimensional grid, and that's going to implement the convolution on this manifold. Now, because of this issue with pixels occurring in multiple charts, we need to choose for each pixel on the manifold which chart we consider to be the canonical chart for that pixel, which holds the ground truth correct value for it. And then before we do a convolution, we need to copy pixels from another chart so that every pixel has valid neighbors. I'll explain more in a second. So this is called G padding. So what you see here is as you transition between these charts, there's a change of direction. So for instance, this green line here is oriented in a horizontal direction in the bottom chart, but when you go to the next chart, it's oriented diagonally. So we indicate this by the +1, which corresponds to +1 times 2 pi over 6, 1/6 rotation. And so our structure group in this case is the group C6, 6-fold rotations, and on this side we see the opposite change of orientation. Now, as I mentioned, for each pixel, there is exactly one place in the rectangular array where its value is valid. So if we zero out the border pixels, the layout looks like what we see here on the left. Now, if we were to apply standard conv2d on this grid, we would run into a problem because any pixel on the edge of a chart, like say this green pixel in the top right, it has a bunch of neighbors that are 0, that have invalid values. And that's an artifact of the way we represent this signal in multiple charts and squash everything into a rectangular array. It's not true that on the original shape, or icosahedron, there were black pixels around. So what we do to alleviate that is to pad, because the pixel that neighbors the border pixel actually is also present in some other chart somewhere in this array. So we simply copy over those values, and when they are not scalars, we additionally have to take into account the gauge transformation between those two charts. So we have to transform the numerical representation of the feature, and that gives us a padded array, where now if we apply convolution with a 3x3 kernel, then every pixel that is in the border of the chart, though not in the border of this array, will have a valid value. So the other aspect of the algorithm is this kernel constraint, and this we've seen come back many times. Only now we have this kernel constraint for a filter that lives on a hexagonal, or the dual of a triangular grid. And so there's actually a way to implement that hexagonal convolution efficiently using square grids and conv2D. And the kernel constraint is similar to what you saw in the previous lectures. Yeah, I'm going to skip over that. There's also a method we developed that works on general meshes. So the previous one was for a very particular mesh, this icosahedron, and it's very efficient. But we would also like, for example, for problems like shape matching, to have something that works on general meshes. And so what we did in this project is to try to define a gauge-equivariant convolution that stays very close to the very simple kind of message passing graph CNNs, but incorporating the geometric structure of a mesh as well. So this approach again uses geometric features, so features that transform according to some representation of the structure group. And the way that manifests in practice is that those features are represented relative to gauge, and the gauge is just a reference neighbor. So here we see a small piece of mesh, and we could, for instance, choose the red neighbor as our reference neighbor, and provided we have an orientation on the manifold that now allows us to express any other neighbor by some angle relative to the first. And so we can define our kernel as a function of the angle. But of course, because the reference neighbor is arbitrary, we need to have some kind of gauge equivariance constraint to make sure that we don't get arbitrary results. Now, this whole field of gauge equivariant CNNs is still in its infancy, but there are already a couple of interesting works, in particular from the field of physics, various works on sampling using gauge equivariant flows, flow-based models for equivariant flow-based models for lattice gauge theory and other lattice gauge theory applications. I have to say I'm not a big expert on the physics applications, but these are potentially interesting for some of you. And other than that, there's a number of theoretical works that try to give a clean description of this general structure. There's a recent paper by Maurice Weiler on coordinate-independent convolutional nets. There's two papers from on the geometric deep learning and equivariant neural nets and homogeneous vector bundles and G-equivariant convolutional neural nets. And finally, there's my PhD thesis, where in part 2, I give a very general account of the gauge theoretical gauge CNNs and other related methods. All right, so I wanted to give a very quick sketch of the underlying mathematical theory of fiber bundles, and I'll probably go a little bit over time, but I hope that's okay. So the goals for a general theory is that we would like to describe in a unified ways convolutional nets on various domains. So homogeneous spaces, we've already seen those, as well as general manifolds. And we also want to cover different kinds of symmetries. We want to treat global symmetries like the rotation of a sphere, and also gauge symmetries that we've been talking about today, both internal and external. And we would like to obtain some generic theorem that proves a universality result. So it tells us any linear layer between spaces of fields on either of those kinds of spaces that's equivariant to either whatever kind of symmetry we like is going to be a function of a certain form, typically some kind of convolutional form. So the main mathematical gadget that we'll use to derive this is the notion of a fiber bundle. So the mental picture that you can keep in your mind is that we have some base space. That's what we've been calling omega, or we could call it B to remind us that this is called base space. This is let's say our manifold. And at each point in the manifold, we have a fiber F. Typically, all the fibers are the same or isomorphic. And together, the base and all the fibers together, they form the total space E. So the way to define this mathematically is actually very simple. We define a bundle via a mapping called a projection map pi that maps from the total space to the base space. So it takes a point on a particular fiber and it maps it to the point over which that fiber lives. So E is the total space, omega is called the base space, and pi is called the projection of the bundle. And another way to indicate what the fiber is to say the fiber over U, indicated by EU, is the inverse image of U under the projection. So all the points in E that map to U, those are called the fiber over U. Now here's everyone's favorite example of a bundle, the first non-trivial kind of bundle. Where we have as a base space, we can take a circle, and as fiber, we can take a line segment. And at each point of the circle, we attach a line segment, but now we see that there are multiple ways to glue these together. We could form in this way a cylinder, which would be called a trivial bundle. It's just topologically speaking, it's a product of the base space and the fiber. But this Möbius strip you see is not the same as a cylinder, even though it has the same base and the same fiber. So it's glued together in a different way. Now, what is typically assumed in the theory of fiber bundles is that although this bundle is not globally trivial, it's not globally a product of base and fiber, it should be locally the product of a base and fiber. So if we take a local piece of the base space, a small segment of the circle, and we look at all the fibers over the points in that segment, we can sort of twist that and make it equal to this arc piece of the circle times the line segment. So that's called local triviality. Now, one important notion that will play a role in multiple ways is the idea of a section. So if we have a bundle, what we can do is we can simply pick in each fiber a particular value in that fiber. So it's kind of like a function, except that the output is in a different in the fiber over the input U. So the formal way to specify such a thing is to say a section. This is called a section. It's a function from the base space to the total space, but not an arbitrary function. I can't map this point in the base space to some point in another fiber. I have to map it such that when I apply my section and then my projection, I get the identity on the base space. So I start here, for instance, in the base space. I choose a point in the same fiber. And of course, the projection will map that point back to the same point in the base space. So that's how you formalize this idea that the section should pick some value in the same fiber, in the same fiber. So there are two kinds of bundles that play an important role in this theory: principal and associated bundles. So on an intuitive level, a principal bundle is a bundle of frames. So we have our base space, and at each space we have a fiber, and in the principal bundle describes this in the fiber the space of all frames for our feature space. Now, any two frames will be related by one and exactly one transformation from the structure group G. Two orthogonal frames will be related by an orthogonal transformations. To oriented but otherwise general frames will be related by a linear transformation with positive determinant, etc. Yes, sorry. Is there a question? If not, then I'll continue. Sorry. So for a section of a principal bundle, that's another word for a gauge, right? If the principal bundle is a bundle of frames and a section picks for each point an element of the fiber, then choosing a section is like choosing a gauge. And then the second kind of bundle we're interested in is called associated bundle. It's a bundle associated to a principal bundle. And this is a bundle where the fibers are vector spaces. Basically, you can obtain this by replacing the fibers of the principal bundle by vector spaces. Now, these fibers, they transform according to some representation rho of G. Applying that representation corresponds to changing the frame of the vector space. And sections of this kind of bundle is what we call fields. So I'm going to skip the mathematical definition of principal bundles, but you can look this up if you're interested. There are two kinds of examples of principal bundles. The first is the bundle of frames of the tangent spaces of a manifold. That's what we've been talking about mainly today. But the other example is the example of a group H with some subgroup G, which forms also a principal bundle over the coset space. You can read more about this in my thesis, as well as several of the other references I mentioned before. So the nice thing here is these are two rather different looking structures, but they're both principal bundles. And that's what allows us to give a unified description of gauge-equivariant CNNs on manifolds and homogeneous CNNs on homogeneous spaces. Various things I'm going to skip over as well. But the other thing I would like to mention is that all notions of symmetries that we've discussed, including global symmetries like translations, rotation of the plane, of the sphere, as well as gauge transformations, they can all be described in a uniform way as principal bundle automorphisms. So certain kind of transformation, certain kind of symmetry of your principal bundle. And then you can prove in a generic way the universality result for generalized CNNs, which shows that equivariant linear maps can be expressed as some kind of convolution-like integral with a kernel that satisfies a certain invariance constraint. Now, I know this is pretty vague, but to give you the full detailed theorem would take much more time than we have today. All right, so finally, here we have and then an overview of the different kinds of generalized CNNs, starting with group equivariant nets that work on homogeneous spaces and groups, but only take into account scalar fields and global symmetries, to steerable CNNs, which also work on homogeneous spaces, but can deal with more general kinds of fields, still incorporating only global symmetries. On the other hand, we have manifold CNNs that work on arbitrary Riemannian manifolds and can deal with scalar fields, and they have, as Michael was explaining, invariance to isometries. And then at least the general theory of gauge CNNs applies to Riemannian manifolds, or even more general settings can take into account general fields and global and gauge symmetries. And there's a universality result for this very general setting. All right, so with that, I'll wrap up, and I'm happy to take questions.